Hi, my name's Tim Halcomb, and I'm going to derive the Taylor series, and I'm going to show people how to expand the sine function into the Taylor series so that you can actually calculate by hand any trigonometric value, like sine 30 degrees, but you have to convert all the angles to radians first, which is very easy to do. So this means that if you do not have a calculator, you can still find trigonometric values, okay? Actually, this is how the computer and calculators do the function, okay? So to get started, let's suppose that you have a function that is continuous and has a limit, okay? So that you can take derivatives of this function, okay? Now, that's quite an assumption, I know, but I could prove it, but that would take up so much time. And by the time I got back to this, everybody, I think, would be bored. So I'm not going to go there. But anyway, I'm going to show you how to expand the function into a Taylor series, okay? Okay, the first thing you need to do is look at f of a. Okay, f of a is going to give c naught. Okay, and then take the first derivative with respect to x, and that's going to get rid of c naught here, and you will have c1. Okay, plus 2 times c2 times the quantity x minus a. If you use the chain rule, think about it. You set u equal to x minus a, du dx is just going to be 1. So you just be multiplying by 1 each time if you use du. Okay, so plus 3c3 x minus a quantity squared. Okay, and now if I set x equal to a in f prime, what's going to happen? Well, that's going to go to 0 because a minus a is 0. So if x is equal to a minus a equals 0, a minus a equals 0. So all you're going to have left is f prime of a equals c1. And then I take the second derivative of x, and I will have, c1 is going to go to 0. So I'm going to have 1 times 2. I'm writing it this way for clarity. Times c2. Okay. And that would give me, plus I would have a 1 times 2 times 3, really 2 times 3, using the chain rule, times c3 times the quantity x minus a. Taking the derivative diminishes this exponent by 1, okay? And so on. So here I would have f double prime of a. I don't even have to write it out because in all the x minus a's, if x equals a, it's going to go to 0, right? So f double prime of a is going to equal to 1 times 2 times c2. 1 times 2 turns out to be 2 factorial times c2. So you could say c2 equals f double prime of a divided by 2 factorial. Okay, and then taking the third derivative of x, taking the third derivative is going to give you equals 1 times 2 times 3 times x minus, sorry, times c3 plus whatever you have here with x minus a's, okay, which you would have just this c sub n x minus a to the n minus 1 each time, right? Because c naught C naught here, I mean, if x minus 1 is to the 0 power, here it's to the first power. If it's a 0 power, C naught times x minus a to the 0 power is just going to be C naught again. So if it's to the 0 power, it's just going to go to 0. So, okay, I mean, go to 1, sorry. So f triple prime at a will just give 3 factorial times C3. So C3 is going to equal to f triple prime at a divided by 3 factorial. Okay, now what do I want to do? I want to plug everything back in here. Okay, I know that f of a is just going to be C naught, right? So I'm going to plug everything back in here. Instead of putting C naught, I'm going to write f of a. So I'm going to rewrite my function, replacing everything, all the c's with what I calculated for the c's. Okay, so C naught is just going to equal to f of a plus C1 times x minus a. And what did I get for C1? F prime of a. Of a. Okay. Times x minus a to the first power, if you wanted to write it. Plus f double prime of a. You could write this over 1 factorial, and you know, it's the same thing. This one is going to be f double prime of a over 2 factorial times the quantity x minus a squared plus f triple prime at a of x minus a cubed. Okay, and this is going to be over 3 factorial, like that. Okay. So what I'm doing here is what I'm trying to do here is formulate a relationship, which I just did with the Taylor series. I'm turning it into the Taylor series. Okay, so this is the Maclaurin series, and the Taylor series is used to derive trigonometric functions, which I'll show you how to do that. How do you turn it into a Taylor series? Well, you just set a equal to 0. If a is equal to 0, then you have what is called the Taylor series. So if you set a equals 0, and you go back to this original function, and you write f, let's put that in there, f of 0 plus f prime of 0, f prime at 0 times x, because x minus 0 is just going to be x again, plus f double prime at 0 of over 2 factorial times x minus 0. This is going to be x squared, x minus 0, sorry, it's going to be quantity x minus a squared, but at a equals 0, so you're just going to have x squared, plus f triple prime over 3 factorial of 0 times x cubed, and so on. This is the Taylor series. And it is how trigonometric functions are calculated on your calculator, on your computer, everything. So you start out, and all this is going to equal to f of x, your new f of x, okay? Let's up with my pencil, okay? That's going to be your new f of x, okay? This is the Taylor series, so I can do that. This is your new f of x. F of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. Okay, so you're going to start out letting f of x equal to sine x, like that. You start out like that, f of x equals sine x. And you say f of 0 equals 0, and f prime at x, f prime, which is the first derivative. Okay, so that's going to be the first derivative. F first derivative of x is going to equal to, the first derivative of sine x is cosine x. Okay, I'll erase that. I don't know what happened there, but that's fine. We can continue. Okay. Okay, so f prime of x is going to be cosine x. And what's f prime of 0 going to be? Well, cosine of 0 is 1. F double prime of x equals negative sine x. And f double prime of 0 equals 0. F triple prime of x equals minus cosine x. And f triple prime of 0 equals negative 1. So I'm going to come back up to my function. I'm going to say, oh, the Taylor series for the sine function. It's going to be interesting because if I continue on this pattern, see the pattern I'm getting? I'm getting let's see. I'm getting odd functions. Odd, okay? So in other words, f of 0 is just going to be 0. And for my x's, okay, for my x's, it's going to be the power of each x is going to be odd. So it's going to be 2n minus 1 for n. Okay. So what I'm going to have here is it's going to be odd. Okay. So I can automatically generalize looking at this. F of 0 is 0. So I don't have to write it. F double prime of 0 over, let's say f of 0 is 0. F prime of 0 is 1 because the cosine of 0 is 1. So f prime of x equals cosine, and cosine of 0 is 1. So I just have my x left over. Minus, well, when I take the triple prime, I get a negative cosine. That's why it's minus. See what I'm saying? So, I mean, I got a plus here, plus f triple prime of 0 over 3 factorial times x cubed. Well, this f triple prime of 0 over 3 factorial, f triple prime of 0 is the same thing as saying minus cosine. Remember, I calculated f triple prime of x equals minus cosine. And I plug in a 0 there, and I get a negative 1. So, and it's next to this x cubed over 3 factorial. So what's going to be the next one? Next one's going to be positive x to the 5th over 5 factorial. And if you want to expand it out, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So that's going to be how you derive the Taylor series for the sine function. Okay, so with that said, if you're going to find the sine of an angle like 30 degrees, well, you can't do it in degree form because this function is in terms of a series, and the series can only be expanded in terms of radians. So you're going to have to convert this, like if you did it 30 degrees over 1 times, for every 2 pi radians in a circle, there's 360 degrees also, but the 2 is going to go into 360 180 times, so you'll have pi over 180 to convert it to radians. 30 goes into itself once, 30 goes into 186 times. So you're going to have 30 degrees, 30 degrees is equivalent to 30 degrees is equivalent to pi over 6 radians. So you have to be in radian mode for this to work. Or if you want to calculate it by hand, you have to convert these degrees to radians like I did. And then you divide pi by 6 and you plug it in for x. And when you plug it in, this will approximate 0.5. And the farther out you go in the series, the better your approximation gets. So remember that the farther you go out in the series, if this is your Taylor series, the farther you go out in the series, the better the approximation get. So if you're finding the sine of pi over 6, and you plug in for x, pi over 6 minus pi over 6 cubed, divided by 3 factorial, plus pi over 6 to the 5th power, divided by 5 factorial, minus pi over 6 to the 7th power, divided by 7 factorial, plus pi over 6 to the 9th power, divided by 9 factorial, you will approximate 0.5. And the more you go out, the better approximation you have. So in general, when your calculator, if you take a calculator and you want to know the sine of, let's say, 38 degrees with your calculator is going to go like this. It's going to say 38. First thing it's going to do is going to convert radian to radians. Even if you're in degree mode, it'll convert it to radians automatically. It'll say 38 over 1 times pi over 180. 16 maybe? No. What am I saying? That'd be that. Okay, like 2 goes into 38. Okay, yeah. Okay. So and the same thing is like 19 pi over 2 goes in 90, right? Yeah. So your calculator is going to see it like that. And it's going to say sine x. Your calculator does this. And it equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. That's how your calculator calculates that with a Taylor series. And it will plug it in this way. It will plug in 19 pi over 90, and it'll say that equals 19 pi over 90 minus 19 pi over 90, 19 pi over 90 to the 3rd power divided by 3 factorial plus 19 pi over 90 to the 5th power over 5 factorial. And it'll just keep expanding it out. I'm not sure how far out in the series the calculator expands it, but I think pretty far out. And for a calculator, that's no problem at all. So you would be able to find that. And just like I said, a sine 30 degrees is like, okay, this is degree mode. If you're in degree mode on your calculator and you hit sine 30 degrees in degree mode, it'll be 0.5. If you hit sine pi over 6, you have a scientific calculator, and you have to be in radian mode. If you hit pi over 6 in radian mode, on your calculator, that will also equal to 0.5. But if you have sine pi over 6 and you're in degree mode, you get the wrong answer because you'll be trying to calculate this in this much degrees, which is different, okay? Remember, 30 degrees in degree mode is the equivalent of pi over 6 in radian mode. Okay, so that's your Taylor series. The Taylor series takes the Maclaurin series and sets A equal to 0. Okay, so you have f of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x to the third power, and you just expand it out as far as you want to go. The calculator expands it out pretty far. Okay, and when you plug it in, you take successive derivatives of sine x and calculate that value for f of 0, and then you plug it back into the Taylor series, and you get sine x equals x plus, there should be a plus sign there, x plus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th. Sorry, that's not, wait, that's minus, sorry. Yeah, it's minus. Okay, sorry. Yeah. Okay, that's supposed to be minus. So x minus x to the third power over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. That is called the Taylor series, okay? So once again, you have sine x equals x minus x to the third power over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial plus x to the 9th over 9 factorial. For small angles, this just doesn't all matter as much because you can just take the first digit. But as the angles increase, the error increases. So this takes care of the error and gives you the accurate value for the sine function. So that's a Taylor series. Remember, a Taylor series takes the Maclaurin series and sets A equal to 0. And you get the Taylor series. So you get f of x equals f of 0 plus f prime of 0x plus f double prime of 0 squared over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x to the third power. That gives you the Taylor series, and you can expand the Taylor series as sine x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Okay, that pretty much covers it.